All right, so today we're going to be talking about race conditions. And before we really get started, I want to just point out that a lot of this is going to be, well, pretty much most of it is based off of the Portswigger both Academy module and their different labs for their race conditions topic. And the higher level like methodology and techniques that we're going to be talking about are from a talk from James Kettle that's really awesome. I really suggest you watch it. He gave it at DEF CON this year, Black Hat USA, and I think a few other conferences. But it's called Smashing the State Machine, the True Potential of Web Race Conditions. And it's just super cool to watch. So if you're interested, I'll link it in the description, but it's also not hard to find, if you look around for anything about race conditions. But highly recommend it. Super awesome and informative video. And yeah, that's really it. But I guess without any further ado, let's just go ahead and start talking about this. So what are race conditions? Well, we kind of have to talk about a few different things. First is if multiple distinct threads are trying to access or interact or change data at the same time, we would call that a collision. And then threads are just, think of them as instructions that are part of a process. So race conditions are just when you specifically time your requests to an endpoint or your actions to cause a collision of data that's being modified. And the impact examples that I've got here will kind of tell us what that looks like. So the impact is also kind of, race conditions are really closely related to business logic flaws because they have to do with these like multi-step processes sometimes. And so the impact is very dependent on the context of the race condition that's being exploited. So if it's like an online shop, the collision might be whether or not the shop is checking. Let's say you add something to your cart and then you click the checkout button. So the application has already written in what your cart looks like and has verified that you have the balance to pay for it. Let's say that you very quickly pressed checkout and added something to your cart at the exact same time. The application might not be fast. It might be fast enough to write in that, okay, you added this to your cart, but that verification that you have the balance to pay for it might be done at a different time. And so you might be able to check out without actually having the funds to pay for the item, which would be a big problem because then you're able to order something you can't pay for. There are also, would be examples like leaving likes on social media or leaving reviews. It should be a one-to-one user. One user can like one thing, but if you can submit enough requests at the same time, maybe it doesn't process it correctly. Or password resets. You might be able to manipulate, email requests, two-factor authentication type stuff, or even the forgot password functionality by utilizing these. So these are kind of, far and wide, and they're relatively common. It's just that they're kind of difficult to find. But this talk kind of uncovers a methodology on how you might be able to find more. And we'll start by talking about like the tried and true example, which is limit overrun race conditions. I don't totally understand why they're called limit overrun. I think I get it, but it's kind of complicated to me why they're called that. But anyway, imagine, right, we're redeeming a gift card. And the application should, when you try to redeem a gift card, check and see if it hasn't been used. It says yes, okay, we'll go ahead and add that gift to your account. And then it sets the gift as being used so that when you try to redeem the same gift again, those checks will return false. However, if you haven't used the gift card before and you try to submit them both at the exact, or submit the same gift card at the same time with two different requests, they both check at the same time. Hey, has this been used? Well, they'll both answer no, hasn't been used. So then they'll both correctly add the gift card balance to your account. And then they both set the same piece of data, the collision. They'll both set that same piece of data to say that the gift has been used. So it's because you're beating the speed at which that information can be processed. But the race window that we're talking about where that collision is taking place is it's between when this not used check happens and when the gift is set to being used. The window it takes, or the time it takes for the application to process all those things is what we'd call our race window. And the collision is, a race condition is just your ability to actually find that race window and trigger a collision that achieves an undesired result. This technique can be pretty wide in terms of like actually finding stuff with it. And the ability to like detect, limit overruns and exploit them is pretty straightforward. Just look for an endpoint that has some kind of useful purpose or a secure function. So like a password reset or, checking out your card or adding a promo code or something. And then just send that request a bunch of times, maybe with different sessions, maybe with the same session. or something along those lines. And really that's, the meat and potatoes of the limit overruns. The problem with those, and the reason a lot of people, I suppose, don't find these, is because there's complications that are not really in your control all the time as an attacker anyway. So latency, right, is the time it takes for your data to arrive at the client. So that's also part of the reason it was really difficult for me to find CTFs that work for this. I found a Hack the Box challenge called Diogenes' Rage that's retired, but it has you exploit a web race condition. But the problem is if you have, worse internet than others and you have bad latency or, kind of difficult jitter problems, it's not going to work for some people and it'll work fine for others. So that's just something to keep in mind. And then the jitter is just the delay between two packets. So, if I send two requests, one right after the other, and they're in different packets and they get processed at different times, that's once they've already arrived there, or they get processed at different times, that's not something I'm in control of really. So now we can kind of talk about fighting jitter. For HTTP 1.1, last byte synchronization is a technique that just withholds the last byte of a group of requests and then sends a final request or a final packet that contains the last byte of each of those requests so that they all kind of get completed at the same time. Smashing the State Machine, that talk I mentioned at the beginning, talks about combining multiple requests into a single packet, which is why it's called a single packet attack, which will effectively eliminate jitter. So you can do this in HTTP version 2, where you're basically just sending one packet that contains 30 requests. So, there's no latency between when those different packets are being processed because they're all being delivered at the exact same time. When we talk about multiple endpoints versus single endpoints, there's some pros and cons. A multiple endpoint race condition, like if you have like the shopping example I was talking about, where you add something to your cart or remove something from your cart before you check out, those are multiple endpoint API queries. And it's easier to kind of trace or understand that exploit because those different steps are observable. But you might have to deal with a few different quirks like connection warming, which is, maybe you'll send a GET request to the home page so that your, it might reduce jitter a little bit, or it might just make it easier for you to send those other requests and to get them, how do I say it? It might be able to normalize delays you might get in processing times. You also might run into rate limiting. So if connection warming isn't helping you normalize your delays, you might be able to, the countermeasure to connection warming is implementing backend delays. So some web servers will delay processing requests if you send too many requests at once. The thing is, if you can intentionally trigger a rate limit and then send your race condition exploit packets, then you know that once you're being rate limited, all your packets that are still being sent through should be treated, or they should be processed at the same time, just using that server delay that's being implemented. So you can kind of eliminate, external delay that way. Single endpoint race conditions, you still have similar issues, but because it's just this one endpoint that you're using to trigger it, it's a little bit harder to gather information about the different state changes. So you just have to be more vigilant when dealing with single endpoint race conditions. And before we get into the lab, I want to talk about the methodology that's described in the smashing or the state condition talk that I mentioned. So it just follows these three: predicting, probing, and proving. So when you're trying to look for a race condition, you might want to ask if it's important, because a lot of endpoints could be vulnerable to race conditions. So you really only want to look for the ones that are maybe useful or have some kind of security impact. And then you want to start asking the questions of whether or not a collision is possible. So try and map out the how you think the expected behavior works, and then follow that up with probing, which is just, maybe sending 20 or so or 30 or so different requests in sequence to see if the application behaves the way you expect it to. And if it does, cool, at least you know what's expected of the application. And then you can try and actually make little adjustments, like maybe sending those requests in parallel and seeing if you see discrepancies between those requests. And then proving it is once you've actually found a race condition, just start removing things that aren't important. So requests that maybe aren't actually that important to exploit the race condition as an effort to try and help you figure out why the race condition is there, so that when you actually report that finding, you're not just telling them that there's a problem, you're actually giving them some kind of help as to coming to a solution. But like I kind of mentioned earlier, there's no, I couldn't find like a hack the box challenge. Well, I could find one, but there weren't really any machines that had like Linux binary race conditions. So this is the best one that I came up with, but there really is nothing that beats the ones on Portswigger right now. I couldn't find any that were better. So we're just going to go ahead and hop into one of those, and then we'll come back here and talk about prevention. All right, so here we are in my Kali Linux virtual machine. I've gone ahead and spun up the lab that we're going to be going through, and without any further ado, let's just start. We were told about this lab beforehand that we're supposed to exploit a feature that lets us change our email address. Specifically, there's a user named Carlos who has yet to register his account, but if we have an email, his email address is carlos@ginandjuice.shop. And if we have that email address associated with our account, it should grant us admin privileges. So we're given a login here that we can use. And you can see that we also have this exploit server. Let me make this a little bit larger here so it might be easier to see. We have this exploit server here where if I just change my email back to what it was, you'll notice it wants us to click a link in our email. And if I just refresh this, you can see it sent us an email. Here's the address it's sent to. And in the body of the request, or not the request, the email, they even say who they're trying to send it to. So we can go ahead and confirm it. And it says our email was successfully updated. I'll go ahead and just click back. And then here, if we refresh the page, you can see that it updated our email back to what it already was. So what we're going to start with is just trying to map out what's going on. So let's see if we can figure out some other stuff. Let's try, we'll go ahead and update this twice. I'm just going to do, let's say +1. And then we'll just try another one that's the same, and we'll see what happens. So you can see we get 2 separate emails. Let's see if this older one works. Okay. So whenever it creates a new link, it looks like it invalidates the old one, which is probably important. Or no, it's definitely important. And there we go. It looks like we updated it back to where it was. Okay. So the process seems to be, we ask it to change the email. The application is writing that email down, probably in a database somewhere. And then it's using that email address to do something. Let's see. Okay, so what we're going to do is make sure I've got my intercept turned on. And I'm just going to capture one of these requests here. Got to make sure that it's okay. All right. What I'm going to do is I'm just going to benchmark this. So I'm just going to send this to my repeater like 10 more times. And in this case, we don't need to do so much, what's the word? Probing, I guess. Or no, we need to kind of, we don't need to predict as much because they told us that this is vulnerable and there's some way we can take control of another email account. But you get the idea. So let me just go ahead and create a tab group. We're just going to call this benchmarking, make it blue. And I'm just going to add all these tabs to it. The reason I'm adding these tabs to a group is not just because it organizes it, but it allows you to send packets in different groups. Because this is HTTP 1.1, I don't think it'll do the single packet attack, but we can still send things in parallel. So first, I'm just going to try and send these, or actually what I want to do is, that's a +1. I'm going to go through these requests and rename each of them. So let's do 2. That's going to be really tedious. Whatever. We'll actually just do it in the name themselves. 5. 6. Okay, so some of those email addresses aren't even for us. But we'll go ahead and send these in sequence. And then we'll go back and look at our emails. Let me just go back to the home page here. Okay, so you can see we got a bunch of emails, and all of them that did go through seem to be... Oh, wait, that's interesting. That's not really our email address. Hang on. I'm just going to send this to the repeater. Bring it outside of this tab group. Let's go ahead and make this yellow. So I thought that was interesting. What this does is this should just send a request for +1. Let me try and I'm going to get rid of the subaddressing real quick because I think that might be confusing me. Send this again, refresh it. Okay, it sends it to Weiner or Wiener. I'm not sure if that's the correct spelling. And confirms it. Okay, now what I'm going to do is I'm just going to make a few extra ones where I just change the actual email address. So something that belongs to 2 or 3 shouldn't be sent to us. Let's just go ahead and we'll send it in sequence again. We'll refresh this. Okay, so... Oh, wait, no, this is going to take anything that's being sent to exploit server. Okay, that was me freaking out about something that's not real. What if I just change this whole thing and change it to the target, which is Carlos at... What was it? Gin and juice .shop. And we'll just send these as a group in a single connection. And we should not see that email come up in here because it should just have sent it to his email, which makes sense. Now, if we try doing these in parallel, or actually, let's go ahead and do the benchmarking ones because some of these are different. And we'll go ahead and do these in parallel. And something you'll notice, like this was sent to +1, but the body of the email says that it's for 6 + 1. So there's a discrepancy between the actual sender and what's being written here. And we see, the same issue here. It's actually identical. We can see 3 + 1 and 6 + 1. So that's kind of odd that it's sending it to different email addresses, but the body is still the same. And this should be tipping you off that there's a race condition, specifically what might be happening. So here's a picture that I drew that kind of describes what's happening with the race window. So when we send 2 requests with different email addresses at the same time, it updates first a database value that's the email address that you're trying to change. And the email operation that is being done in probably a separate thread that edits the database is first sending, filling out, okay, we're going to send this email to this address. And then it waits for the template to be filled out. And between the time that this recipient is selected and the template is being made, or the template is being filled out with the correct reset link, we can overwrite this value in the database, which would then mean, or that would at least explain why we're getting certain emails that have one recipient and a different link for the reset. So now that we've kind of benchmarked it and we've probed around a little bit, let's just go ahead and see if we can replicate the same thing with Carlos. So we've got, 3 requests here, and one of them is for Carlos. So we can try and request these in parallel. And we'll just go back to our mail server. And perfect, right? This got sent to our account, but it looks like there's a link to reset the Carlos user. So it says that our email has been successfully updated. If I go back to our update or our account page, now it looks like our email has been changed to somebody else's email, even though we don't have access to his inbox. And we can now access the admin panel and delete the Carlos user to finish the lab. So That's kind of an example, but the hard part about like demonstrating this is without the single packet attacks, it's kind of hard for like CTFs to do exercises like this without relying too much on network latency or jitter. And the other, kind of interesting thing about this is just it's hard to show off this stuff without, drawing it out like I tried to, because it's difficult to, work out visually. So that's just something I thought I would include. But yeah, we'll go ahead and pop back into prevention techniques. All right, so now that we're finished with that lab, we can actually go into our prevention, which is kind of straightforward if you're a developer, but maybe a little bit more complicated otherwise. But, try to avoid mixing data from different places, or like when we saw, right, is a few different like lookup stuff could cause unwanted changes, but avoid mixing data from different processes or that might be handled by different threads. Try to maintain like atomic state changes. So like, once something is changed, it should not be able to be changed, I would say, in the same process. Try to take advantage of column uniqueness constraints. Try not to use, data storage layers that secure other ones. So like don't use a session to try and stop someone from editing the wrong areas in a database. Ensure that your sessions are consistent when they're being handled. And then some architectures you might even be able to avoid server-side states. So like you can use JWTs, which are not like super recommended because there's a whole bunch of vulnerabilities with JWTs. But if you implement them correctly and carefully, you might be able to avoid like race conditions because the state that's being set has nothing to do with server-side computing. So that's all we've got for today. Pretty cool stuff. There's a lot more research to do into it. I strongly recommend watching that talk like I've probably said 100 times, but thanks for tuning in and we'll catch you next time.